wrap this up. And the conjugate base or nucleophile we were using was Cl-. And this carbocation, it does have an empty p orbital. Chloride could come from the bottom, or it could come from the top, but in this case, it doesn't matter which one it comes from. This would be the product that we would get. These hydrogens and this chlorine came from HCl. We had a triple bond, we still have a double bond because we only are reacting or doing reactions with one bond at a time. This is just a very simple practice on what we did earlier this week with regular alkenes. Same pi bond reacts. We get a slightly funky carbocation, but this makes perfect sense from the arrows above in your notes. And this is what we would logically get if we did that. Let's now think about this particular compound. We could actually add another molecule of HCl to it now, or why don't this time in this class, why don't we add a molecule of HBr to it? So we could make this, and then why don't we add HBr to it just for fun? We have an alkene. Alkenes react with HBr. This particular alkene is a little different. It has chlorine attached to it. We haven't done anything like this before, but we know how HBr reacts with alkenes, and even though we've added this different atom here, it doesn't change how we approach the problem. If there's a six-membered ring here, it doesn't change how we approach the problem. If this alkene was inside a six-membered ring, it doesn't change how we approach the problem. All these atoms come along for the ride, and we're only going to focus on this pi bond right here. So let's do this now. This is definitely unsymmetric. Our mechanism would take a pi bond. There's one left. It would do this. I'm going to explore both possibilities at position 1 and at position 2. At position 1, I make this new carbon-hydrogen bond. We have our old friend, the primary carbocation. So please make sure you draw this carefully. At position 2, we'll have a secondary carbocation. If we made our new carbon-hydrogen bond at position 2, then the carbocation is at position 1. So we know we can reject this right away. And now we could take Br minus. We could add it here. And our final product would have both Br and chlorine on one side. And it would look something like this. So we could do this reaction stepwise. We could have added 2 molecules of HBr from the beginning, or HBr then HCl, or combinations of things. So these can be ClCl, BrBr, a lot of different variations and combinations here. These are kind of different carbocations. Primary is about the same. It's attached to 1 carbon, but this is secondary. It's attached to 2 carbons, but it's also attached to chlorine. So on face value, this carbocation is more stable, but I want us to redraw this particular carbocation. Monday, when we regroup after our second exam, we're going to start talking about resonance and working with it more. This particular secondary carbocation, same one as above it, actually has resonance. It has a way that we can stabilize this plus charge even a little bit more. So on face value, this is a little more stable for sure. It's secondary, it's more substituted, has groups donating electrons into it. But this particular compound has a way to further stabilize itself through resonance. Surprise yourself. See if you can draw one mechanism arrow pushing pairs of electrons somewhere, from somewhere in this molecule, that results in a new resonance structure. take a moment to practice this. Resonance isn't a big part of our second exam at all. You used it on your first exam, and it'll be a big part of our third exam. But second exam won't be a big part, but we're going to just practice it today because we're just slowing things down a bit, revisiting some concepts, and I'm trying to be very compassionate and not add too much more to your burden for studying for this exam. But if you know anything about resonance, practice resonance, then there's electrons here, plus charge here. And technically we could share, through resonance, this partial charge onto chlorine. So this is a secondary carbocation with resonance. So it's actually even a little bit more stable than just the picture here, but don't need any knowledge of this to still make the right decision here, which one to pick, right? So this topic I can introduce now. There's no need to panic about it. Don't need to know any of it for our exam tomorrow, but it'll come later again, and I want to make sure you haven't completely forgotten about resonance when we use it together in class Monday. Resonance is a challenging phenomenon, I know that. And so we'll build it and develop it in due course, particularly on Monday. Let's actually keep going here, and let's try and finish up one more topic here, one more idea. Okay. Ashley, do you have a question? No? Then I'm muting you. If you have a question, unmute yourself. Let's actually look at halogenation. This was the second reaction we learned for alkenes. And we're going to apply the same idea to alkynes. I'm going to take the same propyne molecule. Maybe it's easier if I actually draw it in expanded format like this. You guys should know that these two are the same as this. Same, same, same. All three of these things mean the same thing. Okay? Let's take this one here. Let's take Br2. It's done at minus 78 degrees C. Not a radical reaction. Please don't draw radical reactions for our alkene reactions. Don't confuse radical halogenation of alkane with low temperature, not radical halogenations of pi bonds. This pi bond is weak. This is electronegative. This bromine is electronegative too. Would love those electrons. Positive charge would start building up on one of these two carbons. Doesn't matter which one, because when we draw this, we'll have a bromonium ion. This is maybe the most funky thing we're going to draw today. This is a bromonium ion. It's different because it already has a pi bond in it, but it should have a pi bond in it. This mechanism doesn't break two pi bonds, it just breaks one. This is our bromonium ion. If we were doing this reaction in water, it would go to the more substituted side, but we're not going to do it in water. We're simply going to add our other bromide. And for this mechanism, if you show it going to either carbon, it's okay, but technically, it should probably go to the more substituted one. In the end, I won't be able to tell the difference. And you'll see what I mean by that in a moment. But we know that this bromonium ion wants electrons. This is a three-membered ring. It's strained. It's unstable. It's an unstable intermediate. We give it electrons from the opposite side. As these electrons come in from the opposite side, this methyl group is going to move up to make room for bromine coming in from the bottom. And these two bromines are trans to one another because they add by anti-addition. One of the bromides that came in from this side of the molecule, and this one can only come in from the opposite side. So this will have trans stereochemistry 100% of the time. This is similar practice to what we did with bromonium ions and bromine, Br2, on Monday of this week. The only thing different we've added now is an extra pi bond that we just bring along throughout this whole process. Okay, so this isn't very different than what we did Monday. Please try and convince yourself if this is making you feel weak in the knees, starting to have heart palpitations. Please don't call 911. Please take a deep breath and recognize that this is very similar to this. And by introducing it today, it's just a small form of review. I easily could ask you one small question about something like this and reasonably expect that you could extrapolate your knowledge that you worked together Monday and Tuesday with us on to something just slightly different, okay? This particular compound still has a pi bond in it. I'll actually redraw it. I'll redraw it exactly how we put it in our notes. And we saw this in the pre-lecture video. If we wanted, we could add a second molecule of Br2 to this. It'll keep going because we still have one pi bond left. And the mechanism is the same as how we were doing this Monday. It's very, very similar to what we just did moments ago, but we know that bromine adds across this double bond. And once we're done here, in this case, there's no need to write cis and trans anymore, because we've gotten back to a carbon-carbon single bond, and there's free rotation about the middle bond. So there's no point in writing cis or trans here, wedges or dashes. We've now made a molecule where it doesn't matter where we draw the bromine, since this is freely rotating, that we couldn't tell where they were anyway. So here, right here, if you really needed to on your own, you could practice the mechanism for this. How do we get from here to here? But it's really just like what we were doing in class on Monday, honestly. Not any different than that. I'm going to keep going a little bit longer because I just have one more set of slides for us to work through. It should just take a few minutes, maybe 10 minutes, and then we'll probably take a break.